So let's talk about the derivative in general and kind of how we approach it. So let's just look at a very not specific function. So today we have some function that looks like this. So here's f of x. And the idea is that we'd really like to find the derivative of this function, also known as the rate of change of this function, also known as the slope of the tangent line of this function at a particular point. Let's use some different colors here. Let's say it's right about, let's say it's right about here. Let's call that A, and let's call the y value f of A. The broad idea is that instead of just finding the slope of the tangent line, which looks, here's the tangent line, maybe looking like that. What we're going to do is actually start by finding the slope of secant lines. So we're going to say, well, let's look at some other point over here. And let's call this point, let's say it has an x value of a plus h and the y value of f of a plus h. And that secant line has some other slope. In fact, we can calculate the slope of that secant line. The slope of the secant line is how you usually calculate slope. Difference in the y's divided by the difference in the x's, or rise over run, however you like to say it. My connection is unstable. Okay, well, hopefully it becomes stable. So to find the slope of the secant line, it's going to be the difference in the y values, f of a plus h minus f of a, divided by the difference in the x values, which is a plus h minus a. We usually simplify the denominator there and write it as f of a plus h minus f of a, all divided by h. This is also referred to commonly as the difference quotient, right? Because it's the quotient, right? The fraction of differences. And then the idea is if we want to find the slope of the tangent line, what we do is we let this point here move towards that point there. So if we move it a little bit closer, like say it's right here now, well, then if we draw the point there, our secant line, which things are probably going to get a little bit messy here, but our secant line now has a slope that has gotten closer to the slope of the tangent line. And so the way we're going to do this is say, well, do it in red here. The slope of the tangent line is going to be the limit as a plus h approaches a, or in other words, as h approaches 0, because that's what's happening. That's happening here. This distance h is getting smaller and smaller and smaller of this difference quotient. And that's kind of the gist, really, is that to find the slope of the tangent line, which we'll soon kind of just say is the derivative, we're finding the limit as h approaches 0 of this f of a plus h minus f of a all over h. You might notice that if I just plugged in 0 for h, I would get f of a minus f of a over 0, which is a 0 over 0 type of limit, which is why we spent time practicing these 0 over 0 types of limits, because these limit definition of the derivatives are going to be 0 over 0 types of limits. Let's look at a few examples. Let me make sure there's nothing else I want to say here. So just as a point of interest, occasionally people write this a different way. Sometimes people call this point here x, and they call this up here f of x, and they write it as that the slope of the tangent line is equal to the limit as x approaches a of the difference quotient, f of x minus f of a all over x minus a. It's an equivalent way of writing it. Usually we prefer this because it's usually algebraically easier to deal with. But this is also something that you might see occasionally. I don't think either professors did show it this way, but just thought I mentioned because it's often where people start. So let's look at some more concrete examples instead of just having this kind of whatever function here. Let's see, what do I got? Yeah, let's look at this to start off with. So let's look at f of x equal to x squared plus 6x. And for the moment, we'll talk about finding the slope of the secant line. So let's say we want to find, we're going to start off by finding the slope of the secant line on the interval from 1 to 3. Let's draw it. You don't always have to draw it, but it's good to draw it here. I don't know exactly what this looks like, but it's some sort of parabola. It has, I don't know, if there's something else going on over here, I don't really care. It's got this kind of shape. Vaguely. From 1 to 3. Calculation is not terrible, right? Our slope here of our secant line is going to be also known as the, I have to write this down, the slope of the secant line, also known as the average rate of change, is just going to be our f of 3 minus f of 1 divided by 3 minus 1. So in this case, that's going to be, let's see, f of 3 is going to be 9 plus 18 minus f of 1, which is going to be 1 plus 6 divided by 3 minus 1. And simplifying that, that's 27 minus 7, so 20 divided by 2, which is 10. Oops, my pens. So the slope of this line, which I'm drawing poorly here, sorry, the pictures aren't always great. The slope of that secant line is 10. And what we'd really like to do is to kind of see what the slope of the tangent line is at 1. So we're going to get a little bit closer. Instead of going from 1 to 3, now let's go from 1 to 2. All right, well, again, same idea. That's just going to be f of 2 minus f of 1 over 2 minus 1, which is going to be, the f of 2 is going to be 4 plus 12 minus f of 1, which is again 7 all over 1, which is going to be 16 minus 7, that's 9 over 1, which is 9. And you can keep going with it, right? You could plug in values that got closer and closer to 1. But what we really want to do is we want to take the limit as this number is approaching 1. Or as I would prefer to write it, we're going to write the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. So we're imagining some 1 plus h here, and we're finding the slope of the line that's secant between this point and that point. Okay, so we're just going to multiply it out. So we're going to have the limit as h approaches 0. So f of 1 plus h is a little annoying. It's going to be 1 plus h squared plus 6 times 1 plus h minus f of 1 we've calculated twice already. It's 7 all divided by h. And to no one's surprise, if we plugged in 0 right now for h, we'd get 0 divided by 0. So we have to do the algebra. So we're going to multiply at the top. I should have left myself a little more room here. Limit as h goes to 0. I should let's just use, you know what? I can use another piece of paper. It's not a crime. Well, not a huge crime. So we've got, let's see, the limit as h approaches 0. 1 plus h squared, which is 1 plus 2h plus h squared plus 6 plus 6h minus 7, all divided by h. Here's what should usually happen. All of the not h terms should cancel in the numerator. That's what we want to happen. It might take a step or two to get there, but at the end of the day, well, at the penultimate step, the last step before the end of the day, we hope all the not h terms cancel. So that then the rest of the terms in the numerator have an h, we can factor out and cancel the h in the bottom. Here, the 1 plus 6 minus 7 does in fact add up to 0. And we're left with a 2h plus h squared plus 6h. I'm going to factor out an h. Yes, I could add 2h to 6h, but I'm not going to. I got h times 2 plus h plus 6 divided by h. Those h's divide to 1, and then plugging in 0 for the remaining h's, we get the limit as h goes to 0 of 8 plus h, which is just 8 plus 0, which is 8. So what that tells us is that the slope of the line tangent to this curve at that point is in fact 8. Let me write that down. So the slope of the line tangent to f of x equal to x squared plus 6x at the point, or at the place where x is equal to 1, is 8. And then if you're asked, you can also easily find the equation of the tangent line. So just as a follow-up here, the equation of the tangent line we're just going to use the the point slope form. We have the slope, which is 8. We have half a point. We need the y coordinate. So if we plug in 1 to our function, x plus 6x, we know that x is 1 and y is f of 1, which is 1 plus 6, which is 7. So our equation of our tangent line would be y minus the y coordinate equal to your slope times x minus the x coordinate. I kind of like just leaving it this way, but oftentimes we're asked to write it in the y equals mx plus b form. So if we solve for y, we have y minus 7 equals 8x minus 8, and then adding 7, we get y equal to 8x minus 1. So either of these should be fine unless someone specifies how you have to write your answer. Okay. What if I said I then wanted to find the slope of the line tangent at x equals 2? That's a bummer, because it means I have to do all this work again. And then if I said 3, I do it again, and right, every different point, if I do it this way, where I'm just finding the slope of the tangent line at one particular point, requires going through this whole process every single time. So instead, say, well, let's just find the slope of the tangent line at any value of x. So instead of finding the slope of the tangent line at x equal to 1 or 2 or 3 or more generally a, by finding the limit as h approaches 0 of f of a plus h minus f of a all over h, what we eventually move towards is just saying we're going to use the variable x instead. So I'll point out here, yes, a looks like a variable because I'm not putting a number in for it, but we're supposed to imagine like we've put in 1 or 2 or 3. So there's a specific actual number that's going in there. So what we'd rather do is say, okay, well, I'm going to find the limit as h approaches 0 of f of x plus h minus f of x all over h. And then my slope of my tangent line at any point x will just be a function of x, which we're about to call the derivative, but let's hold off for just a moment. So we calculate it that way, same sort of idea. It's going to be the limit as h approaches 0. I'm still, so I should point out, I'm still using the same function. My function is still x squared plus 6x. So I'm just going to rewrite f of x plus h. Let me write that over here. This is a note somewhere over here. Right, my function is still x squared plus 6x. So we're just rewriting this as f of x plus h. So it's going to be x plus h squared plus 6 times x plus h minus f of x, which is x squared plus 6x, all divided by h. I've made a mistake. If I go further this way, my 6x's will not cancel out. And that's a disappointment because I want all the not h things to cancel out in the numerator. So be careful here, right? So I'm gonna leave the mistake for a second, but I'll fix it in a moment. So if I rewrite this as the limit as h goes to 0, if I FOIL this out, x plus h squared is x squared plus 2xh plus h squared. Distribute the 6 plus 6x plus 6h. And if I had a plus 6x over here, I'm not writing the plus sign because I don't want to. But if I had a plus 6x there, those would not cancel. I'd be like, oh, I must have made an error, because what I'm hoping to happen, what should happen, is all the terms that don't have an h in the numerator should end up canceling out to 0. And I need to have minus all of f of x. So the minus sign distributes, and I get minus x squared minus 6x. And then the positive 6x and the negative 6x add up to 0. The positive x squared and the negative x squared add up to 0. And then the remaining terms all do have an h, which I'm happy about. Then I'm going to factor out the h from the top. And the limit as h goes to 0 of x multiplied by 2h. Sorry, factor out the what from the top? I said h, I wrote x. Sorry. Factor out the h from the top. I'm left with a 2x plus h to the first plus 6, all divided by h. Now the h is divided to 1. I'm left with the limit as h goes to 0 of 2x plus h plus 6. The h goes to 0, and I get 2x plus 6. And you can see that if I plugged in 1 for x, my slope would be 8, just like we got before. If I plugged in a different value like 2, my slope would be 10. If I plugged in 3, my slope would be 12, and so on and so on and so on. So what we can say here is that the derivative of f of x equal to x squared plus 6x is f prime of x equal to 2x plus 6. And so that for any value of x, we can find the derivative of the function by just plugging in a particular value of x. Or not, we can just leave it as a function. So the derivative is a function as well that depends on the original function. Something else I want to say here? No. I'm trying to think about if there's not something else I need to say that's important. Don't think so. I mean, there's lots of other things, but not right this moment. Questions, comments, observations?
Do we care about single-sided limit?
No, not really. So occasionally, yes, there's one example I have in mind for a little bit later. But really, the one-sided limits for the limit definition of the derivative only really come up when you're trying to show that the derivative does not exist. Specifically, I'm thinking about the absolute value function, which I'll cover in a little bit here. But generally, no. So what I would say is that we now have a limit definition of the derivative. And this is kind of the first place you go when you're trying to think about what the derivative of a function might be. So for example here, so definition, the derivative as a function of f of x is defined to be f prime of x equal to the limit as h approaches 0 of the difference quotient f of x plus h minus f of x all divided by h. Excuse me. Just want to say a few words to the side for a second. So when you think of a derivative, I imagine, I could be wrong, but I imagine the main thing you probably think of is the slope of a tangent line. And that's a good interpretation, but it's not the only interpretation. A more general way to think of it, which I would encourage you all to kind of begin to wrap your minds around, is it's really a rate of change. A derivative, in fact, I should write that down. It's a rate of change. It's really answering the question, how is something changing as something else is changing? When we talk about functions and graphing them, we're really asking the question, how is y changing as x is increasing? That's what which is another way of saying what's the slope of the tangent line. So you can think of it as how is y changing as x is increasing? Which we often write as dy dx. A small change in y divided by a small change in x. And there's lots of notation for derivatives, which we'll talk more about as we go along. This is pretty typical, so is this. So, oh, sorry, you're way off to the side. Sorry, one second. Where'd you go? Well, we got And think about what I'm saying here. Rapture. Yeah, we can go that way. Yeah, okay, sure. So let's talk a little bit more about these derivatives. So actually, let's go to the example that you kind of, sorry, did I go a little too fast there? Oh, sorry, let me try to leave it. So actually, let's talk about whether a function is differentiable or not. So f of x is differentiable at x equal to a if f prime of a exists. It's a little, I feel like I'm getting a little, all right. Let's look at some examples of functions that aren't differentiable in certain places. So, for example, f of x equal to, I don't want to get too crazy here. Let's see. Sure. The problem is I'm gonna write down the function that we have to take the derivative of. So let's be smart, James. Sure. Let's start with the absolute value one. So f of x equal to the absolute value of x minus 2. We're going to show it, but I'm just going to state is not differentiable at x equal to 2. Graphically, what you should think about is the function not being smooth. So now we talked about continuous, and we talked about how functions continuous. If you can draw it, you don't have to like lift your pen off the paper. Well, there's a similar idea for continuity. And it's not 100% always exactly spot on because there's a couple of corner cases that there's a joke there that you will understand in a second. There's a couple of corner cases where the function is still smooth, but it's not differentiable. But most of the time, we say a function isn't differentiable or isn't smooth if it has a corner, there's the joke, or a cusp, meaning it's pointy. So I usually say a function is not differentiable if it has a pointy point, like an absolute value, like that. That function is not differentiable at 2 specifically. It is differentiable everywhere else. So just like with continuity, we also say something isn't differentiable if it happens to not be differentiable at least one spot. Just like a function isn't continuous if it's not continuous at one spot. Even though, yes, this function is differentiable almost everywhere. So let's talk about finding or showing the derivative doesn't exist. So we're going to start off with the definition. So we're going to find f prime of, so we're actually going to go back to the definition that's at a particular point, not at a general x value. So we're going to look at f prime of 2. So cool, it's the limit as h approaches 0 of, instead of f of x plus h minus f of x over h, it's going to be f of 2 plus h minus f of 2 all over h. All right. So then we're going to simplify this. The limit as h approaches 0. So we're just going to plug this 2 plus h into the function. So it's going to be the absolute value of 2 plus h minus 2 minus the absolute value of 2 minus 2 all divided by h. So then we're going to simplify. We're going to the limit as h approaches 0. The absolute value of 2 plus h minus 2 is the absolute value of h. And 2 minus 2 is just 0. And now is where we do need to look at the different sides of this limit. Because if h is already positive, then the absolute value of h is just h. So we have 2 directions to go here. We have the limit as h approaches 0 from the right side, where the absolute value of h is just good old h. H divided by h is 1. So the limit as h approaches 0 from the right of 1, and the limit of a constant is just the constant. On the other side of 2, or on the other side of h being 0, approaching 0, the limit as h approaches 0 from the left, well, then the absolute value of a negative number is the negative of that negative number. Right? Is h positive or negative? slightly negative. So the absolute value of a slightly negative number, like the absolute value of negative 0.05 is negative 0.05 to make it positive. So whenever you're absolute value of something, and the inside parts we know are negative, even though I'm not actually writing a number there, I have to do the negative of that to turn it positive. But then negative h divided by h is -1. And the limit as h goes to 0 from the left of -1 is -1. And these two limits aren't the same. So what that tells us is the limit does not exist. But the limit was what the derivative of 2 was defined to be, meaning the derivative of 2 does not exist, or the function is not differentiable at x equal to 2. Which we could all see if we look at the graph. And we'll say, so let me ask you all, on the right-hand side, what's the slope of that line? Show me on your fingers. Yeah, the slope of this line is 1, positive 1. How about the slope of that line on the left? -1. And those aren't matching up. For the function to be differentiable, essentially what that means is the slope has to be continuous. And the slope from the right and the slope from the left have a jagged change. If I tried to graph this derivative, fit in here, the graph of the derivative would look like -1 up until 2, and then at 2 we jump from -1 to +1. And that graph of the derivative certainly is not continuous, which means the original function is not differentiable. Or you can say there's a pointy point. Pointy, not differentiable. Got a sharp corner, no way. So, let's see. Yeah.
So if we know that the derivative is continuous, then the original function is smooth.
I would say we know the original function is differentiable, but yes. So I'll point out, while differentiability and smoothness are almost the same, they're not exactly the same. I want to do that example. Yeah, that's fine example. So let's look at another example where the function is smooth, but the function is not differentiable. Yeah.
The absolute value didn't return the h.
So it did because the h here is already negative. So the negative of this negative number is positive. We just have to express it in a way that shows what it is. So this negative h here, even though it looks negative, it actually is a positive number because we already know that the number we're plugging in for h is slightly negative. Like over here, right? This is like our h value. And then the absolute value of that negative number is the negative of that negative number, which ends up being a positive 0.05.
Okay, and then the denominator, we don't plug.
The denominator was just good old h the whole time.
Oh, then we don't plug the slightly negative.
Well, I could, and if I did, I would get negative 0.05 divided by negative 0.05. So I end up having positive 0.05 divided by negative 0.05, which is equal to -1. Okay, two more functions that are not differentiable at a particular point. And again, we're not talking about the general derivative here because they're kind of a terrible pain to calculate. We might do one of them later on, but it's really kind of gross. So let's look at the following two functions. First one that's more obvious. F of x equal to x to the 2/3 power at x equal to 0. I will tell you, it is not differentiable. Let me show you. Here's what the function looks like. I often refer to this as the bird function because it kind of looks like a bird that a not very artistic person might draw, like myself, like this, like that, little birds. And that function is very pointy at the origin. It's got a cusp. And actually, I feel like the difference between a cusp and a corner is one I'm not good at distinguishing between, actually, now that I think about it. But a cusp is more like when you have like a point like this where like your tangent lines get to be very vertical. right? My slope here is actually, I didn't draw it very well, but my slope here is super duper positive. If we try to calculate the derivative, let's see what happens. And again, we're using the derivative at a point. So f prime of 0 is going to be the limit as h approaches 0 of, let's just write the definition, f of 0 plus h minus f of 0 all divided by h. That's going to be the limit as h approaches 0 of f of 0 plus h is just f of h, which is going to be h to the 2/3 power. F of 0 is 0 to the 2/3 power, and 0 to any positive power is just 0 divided by h. We'll simplify. We get the limit as h goes to 0. Let's see, 2/3 minus 1 is negative 1/3, but I would rather write it as the limit as h goes to 0 of 1 over h to the positive 1/3. If you plug in 0, what ends up happening? I get 1 divided by 0, which is undefined. To be a little more specific here, just so you can see it, you actually have a different right-hand, left-hand thing. From the right-hand side, the limit would be positive infinity. And from the left-hand side, the limit would be negative infinity, because a very small positive number, if you take a cube root of a positive number, it's still positive. Take the cube root of a negative number, it's still negative. So it's actually going to be positive infinity from the right, negative infinity from the left. Which if you can probably kind of maybe see by my graphs. On the right-hand side, my tangent lines have positive slopes. And they get more and more steep as they get closer to 0. On the left-hand side, my tangent lines have negative slopes. And they get steeper and steeper as I get closer to 0. So we're getting a slope of negative infinity from the left, positive infinity from the right. And even if they matched, we still wouldn't say that the derivative was infinity, right? That's not a thing we say. The derivative does not exist here. So this function is not differentiable at x equal to 0. I know this is still not an example of something smooth, right? This is a corner, but here's a smooth one that isn't differentiable at 0. F of x equal to the cube root of x is also not differentiable at x equal to 0. For a very similar reason. In fact, you could make almost the same exact argument here. You could say, okay, great. F prime of 0 is going to be the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h, which is the limit as h approaches 0 of f of, sorry, I got carried away here. I started writing too much. F of h minus 0 all over h. And then I should have calculated what f of h was in that step. Oh, well. Its limit as h approaches 0 of the cube root of h all over h. Simplifying that, we have h to the 1/3 divided by h to the first, which is h to the 1/3 minus 1. I really, really, really don't like negative powers of 0. I would much rather write it as the reciprocal thing to a positive power. It's just easier for me to tell what's going on if I do it that way. Because you might be able to fool yourself and say that 0 to the negative 2/3 power is equal to 0. That would be wildly wrong. 0 to a negative power, undefined. Because if we rewrite it, we are much better at seeing that, okay, we have 1 over h to the 2/3 power. If I plug in 0 here, 1 divided by 0, let's see, 0 squared is 0, and the cube root of 0 is still 0. 1 divided by 0 is undefined. I will point out, this function does have a tangent line at the origin, even though it's funky. This has a, so I should just say it here, note that f of x equal to the cube root of x does have a vertical tangent line at the origin. And I'm going to try my best to draw it here. We'll see how this goes. I already drew the tangent line. It's the y-axis. And here's my cube root function. kind of like that. We definitely have a vertical tangent line there. Is the function differentiable at 0? No, because if you think about the derivative being the slope of the tangent line, what kind of slope does a vertical line have? Undefined, rise over run. Okay. Let's see, do you have anything else of real value to say here? Okay. Making sure I'm not missing anything super important here. All right. Yeah, let's see there. So then we typically move on, to talking about making up some of the derivative rules, like the power rule, the product rule, the quotient rule, and eventually the chain rule. So that's where we're going next. Oh, I know that. Sorry. But before that, one more thing I want to say. So sometimes people like to ask a question like, oh, where'd you go? Good example of mine. Sorry, 1 second. I've hidden the pictures from myself. They're all over the place. All right, one moment. Where are you hiding? Oh, I know where you're hiding. So let's say someone gave you something like this. Are we there yet? Sorry. I'm about to say something. I'm not even sure we have the tools. We're not quite there yet. We'll come back to this. Sorry, I thought I had it, but I realized we need to build it more. So we want to find some derivatives. We want to find the derivative of f of x equal to, we'll go full. F of x equal to a constant. So we're going to build up the power rule here in about 3 or 4 examples. Constant's easy. So for every function, unless someone gives you some other intuition as to how to approach it, if they say use the limit definition to find the derivative, you should be just tossing this into that formula. And you should definitely memorize the fact that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. You for sure want to memorize that. So in this case, f of x plus h is a constant. And f of x is the same constant, right? Whether I plug in x or x plus h or 1,000 or 2,000 or negative 1,000,000, the output is always the constant c. Whether that constant is 5 or 6 or negative 2, whatever we pick. But they're the same here. Okay, this is not going to be a 0 over 0 type. Let me show you why. C minus c is 0. Is h equal to 0? It's approaching 0, right? Does that mean it's equal to 0? It does not. It means it's specifically not 0, right? When we talk about limits, we are getting really close to that number, but we're not actually ever getting to that number. So that means that 0 divided by h, well, 0 divided by not 0 is 0. So this is the limit as h approaches 0 of the constant 0. And then as we've seen a few times, the limit of a constant is always just the constant. Or you could just make a geometric argument to yourself and say, hey, look, this line that I've just talked about looks like this. What's the slope of that line? 0, right? Rise over run. There is 0 rise. There's a whole lot of run. The slope is 0. So let's look at the next one. I don't want to do this. Yeah, I'm gonna actually, so let's do this one. Now we're gonna find for the function, instead of doing just x to the first, let's do a constant times x to the first. Bless you. Bless you again. K times x. I know I use c there. I'm using k here. Go figure. So again, same idea. We're going to say great. The derivative. Now, let me just ask you all quickly. If our function is a line that is k times x, what's the slope of that line? K. What do we expect the derivative to be? K. So if you ever have a straight line, whether it's horizontal or tilted, the slope is just the derivative, and the derivative is just the slope. Well, let's do it. So it's the limit as h approaches 0 f of x plus h minus f of x over h. I would say at least the first 10 times you do this, you should write this out. Even though it's the same thing every time, just do it. It'll stick in your brain. You'll know it for sure. It'll be there. I still do it, right? Even when I'm doing fun stuff on my own, I still like, let's just write it out because it's good to remember what we're doing. So then f of x plus h, we're just replacing the x with x plus h. So it's going to be k times x plus h minus f of x, which is k times x, all over h. The kx's cancel. So you're going to end up getting kx plus kh minus kx divided by h. Kx minus kx is 0. The limit as h approaches 0 of kh divided by h. We do the division first. Kh divided by h is just k. And the limit as h approaches 0 of k is not surprisingly just k. And I'll just say more specifically, if your function is just x, sorry, if f of x is just x, what's our derivative going to be? 1, right? The slope of y equals x is just 1. Okay. We'll do 2 more. And then we'll talk. Oh yeah, we can do 2 more, then we can do something fun. So we'll do it for x squared and for x cubed, and then we'll talk about how you could go further, but we won't. So for f of x equal to x squared, we kind of already did one like this back in the beginning of class. Still good to do this. So I imagine many of you already know what the answer is going to be. It's totally fine. I will also point out, most of you will probably have a question on your next exam that specifically says, use the limit definition of the derivative to find the derivative of whatever function. And then although you will know a shorter way of getting there, you will still need to show your work the longer way using the limit definition. So you should definitely be prepared for that, unless your teacher specifically says it won't be on there, which I highly doubt. So here the derivative is going to be the limit. Why don't you guys do this one? The limit as h approaches 0 of f of x plus h minus f of x all over h. I'll write out the next step and then you finish it off. F of x plus h is x plus h squared. F of x is x squared all over h. We'll have to FOIL out that x plus h squared. I'll give you a minute and a half. Tomorrow is 2/5/25. I told you guys about anchor days yet? No, okay. Well, we'll wait until we have one. We won't have one. Well, we'll wait until. Yeah, we don't meet on Friday. Whatever. Some other day I'll talk about it. Anyway, it's been enough time. So we're going to multiply out the x plus h squared. You do want to get real comfortable multiplying out as x plus h squared. It's going to come up very often. It's going to be x squared plus 2xh plus h squared. Thank you. Minus x squared divided by h. As is what we hope for, the non-h things end up canceling out. You can, so I'm going to skip a little work here and say each thing gets divided by h. So I'm left with the limit as h approaches 0. 2xh divided by h is 2x. H squared divided by h is h. And then h goes to 0, so you get 2x plus 0, which is just 2x. Okay, let's do one more, but we're going to make a cool observation. For f of x equal to x cubed, same deal. F prime of x is going to equal the limit as h goes to 0. Okay, I'm going to skip the step of writing f of x plus h. I'm going to write x plus h cubed minus f minus, maybe not. Maybe I'm not going to skip the step. Minus x cubed, sorry. It's a little ugly there. All over h. You don't really need the parentheses around x cubed there. I just started writing parentheses, so I got kind of stuck. There's my f of x plus h. There's my f of x. And now for a trick. X plus h cubed multiplies out as x cubed plus 3x squared h plus 3xh squared plus h cubed. And though I haven't shown you my trick yet, I did use a trick to do that. What's the trick? Well, we'll come back to this in a second. So there's a trick for multiplying out a binomial raised to a positive integer power, like x plus h cubed, or to the fourth, or the fifth, or the sixth, or really any positive integer you like. And it all has to do with something called Pascal's triangle, which I think is super cool. And we'll look at it right now. So here's how it starts. You draw a couple ones, and then on the outsides of the triangle, you're going to have ones the whole way down. And on the insides of the triangle, you're going to take the two things above it and add them together. 1 plus 1 is 2. And then in the next row, 1 plus 2 is 3, 2 plus 1 is 3, 1. And the next row, 1, 4, 6, 4, 1, and so on and so on and so on. And it literally goes on. Oops, that's a 10 out of 5. Forever. Typically, we call this top row the 0th row. So this is the 0th row. This is the first row, second row. And at least for every row beyond the 0th row, the second term in that row tells you the number of the row. Third row, fourth row, fifth row, etc. Okay, here's what's cool about, well, I should say, here's one of the many, many, many things that's cool about Pascal's triangle. Pascal's triangle has so many interesting patterns and numbers that it's just kind of mind-boggling. But I'll point out that if I was to multiply out x plus h to the 0th power, I'd get 1. If I were to multiply out x plus h to the first power, I would get 1x to the first plus 1h to the first, which I know is kind of silly to write all that, but to make a point. And then we just saw that for x plus h squared, it was 1 times x squared plus 2 times x to the first times h to the first plus 1 times h squared. And the pattern here is that, or the way I think of the pattern anyway, is that when you're writing out x plus h to some power, these are the coefficients. You start with x to whatever the highest power is. So I'm going to get 1 times x to the third. And then every next term, I use the next coefficient. The power of x decreases by 1. The power of h increases by 1. So that the powers of each term always add up to whatever that number is, 3 in this case. So the next term is going to be coefficient of 3, x to the 1 less power, h to the 1 more power. Next term coefficient is 3, x to the 1 less power, h to the 1 more power. Next coefficient is 1, x to the 1 less power. I'm not going to write x to the 0th, h to the 1 more power. And you can do that for any power of x plus h. I could quickly say that x plus h to the 4th is going to be, well, I'm going to use the 4th row here. It's going to be 1 times x to the 4th plus 4 times x cubed times h plus 6 times x squared times h squared plus 4 times x times h cubed plus 1 times h to the 4th. Relatively straightforward. This is typically how people actually multiply out things like this, is they don't actually like do the multiplication out. They're thinking of, okay, Pascal's triangle, which row am I looking at? I know if it's the 4th power, I need the row where the second term is 4, and then write all that. So I want you all to take a moment right now and try to write out x plus h to the 5th. It should have 1, 2, 3, 4, 5, 6 terms in it. I'll give you the first one. So here's how we should be looking. 1 times x to the fifth plus 5 times x to the fourth times h to the first plus 10 times x cubed times h squared plus 10 times x to the 1 less power h to the 1 more power plus 5 times x to the 1 less power h to the 1 more power plus 1 times h to the fifth. And then we might as well set us up for success in a minute. If my power was some just large positive integer, I'm going to call p. If I was going to find x plus h to the p, I'm not going to write all the actual numbers because I don't know them and I don't care about them. But what I do care is the following. I know my first term is going to be x to what power? X to the p. And my next term, what's the coefficient going to be? It's going to be p, right? Because just like when it was 5, it was 5, it was 4, it was 4, when it was, right? The next coefficient is always whatever your original power was. So the next term is going to be p times x to the p minus 1 times h to the first. Right? The power of x is 1 less, the power of h is 1 more. And then the next term, I don't want to burden you with the knowledge of what the coefficient is because it's annoying. Later on, if you ever take a stats class or a combinatorics class, come talk to me, we'll talk about it. It's called the binomial coefficient. But the next term, I don't really care. I'm just going to call it c sub 2. So there's some constant. I don't care what it is. And I know that the power of x is 1 less than it was before. So p minus 2 now, or p minus 1 minus 1. And the power of h is h squared. And then we go along. There's a lot more terms, plus dot, 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 all the way till the last couple terms. Well, there is symmetry here in case you hadn't noticed, right? You have 1s at the end and then the 5s and then 10s. So the second to last term is going to be a p times x to the first times h to the p minus 1, because the powers have to add up to p, and 1 plus p minus 1 is p. And finally, the very last term is going to be 1 times h to the p power. Cool, we're going to use that in a minute. So back to the example we were doing before I got on this trip over here. That's how I knew that x plus h cubed was going to be x cubed plus 3x squared h plus 3x h squared plus h cubed. And then just like before, those add up to 0. We're left with the limit as h goes to 0 of, let's factor out an h. We've got h times 3x squared plus 3xh plus h squared, all divided by h. The h divided by h is 1. And then we are left with the limit as h goes to 0 of 3x squared plus 3xh plus h squared. And then that's going to be 0. That's going to be 0. So we're left with 3x squared, which is the derivative of x cubed. And now for the big reveal, which again, I imagine a number of you are familiar with already, but that doesn't mean we shouldn't do it, is that you can actually do this for any positive integer power p. So if I want to say my function f of x was equal to x to the p, then the derivative is going to be the limit as h goes to 0 of f of x plus h minus f of x all divided by h, which is the limit as h goes to 0 of x plus h to the pth power minus x to the pth power all over h. And that's how we just spent a few moments figuring out that x plus h to the pth power is that gross thing up there. It's actually not gross. It's beautiful. We love it. It's very helpful. So then we're going to write out the limit as h goes to 0 of all of that minus x to the p all over h. So we have x to the p plus p times x to the p minus 1 times h plus some constant times x to the p minus 2 times h squared plus all the way to the last couple terms, p times x to the first times h to the p minus 1 plus h to the p minus x to the p power. And just like in pretty much every problem we've done so far, the non-h terms cancel out. In this case, it's our x to the p and our negative x to the p. Every remaining term has an h, which we can factor out. So then we're going to have the limit as h goes to 0 of h times let's see, p times x to the p minus 1 plus some constant times x to the p minus 2 times h to the first plus lots of other terms that have higher powers of h, right? Because the powers of h just keep getting bigger and bigger and bigger. And finally, the last couple terms, p times x times h to the p minus 2, because I'm pulling one of them out, and p minus 1 is p minus 2. And finally, h to the p minus 1, all divided by h. Questions about that? All right. H divided by h is 1. We don't care about 2. And then we take the limit as h goes to 0. So I will point out, you can probably skip the stuff I'm writing. Like, I'm always writing more steps than you probably need to write. That's okay, but just be aware that you probably don't have to write every single step I'm writing. Like, most people be like, yeah, those cancel. The rest of h is go to 0. We get what we get. I like to write this stuff out. So we've got that plus c2 times x to the p minus 2 times h plus lots of other terms plus p times x times h to the p minus 2 plus h to the p minus 1. But then every term after that first term has h to some power. And if we plug in 0 for h, that's going to be 0. All that's going to be 0. That's going to be 0. That's going to be 0. And you're left with just p times x to the p minus 1. Which is known as the power rule. So it is true that if your function is f of x equal to x to some power, then your derivative of that is that power times x to the power minus 1. Or as you say, the power comes down and then the new power is 1 less. It is true. So I'll point out, we've only shown this is true, excuse me, for powers that are positive integers, 2, 3, 4, 5, etc. But it is actually true for any power. Positive, negative, fractional, irrational. Doesn't matter what your power is. It even works if you pick if it's like 0 or 1, although it's kind of silly if it's 0 or 1, you just know. Like if you have x to the first, you know the derivative is 1. If you have x to the 0th, which is 1, you know the derivative is 0. But this is true for any power. So it's true that, for example, if f of x was equal to x to the negative 7th power, then your derivative is going to be negative 7 times x to the negative 7 minus 1, which is negative 8. Even though this work doesn't technically show that that's true, because this pattern that we used only really is true if your power is a positive integer. But the power rule works for any value of your power p. Okay, cool. So power rule, it's a great rule. We use it all the time. Get comfortable with it. Yeah, what do I want to say about that? There's more to say here, but let me see for a second. Sure. Yeah. So one example here. What if I wanted to say find the derivative of f of x equal to x to the 10th plus 1 over x cubed plus the 5th root of x squared. So to be a little bit careful here, I will point out the derivative of 1 over x cubed is not 1 over 3x squared. Right? We can only use the power rule if something is written as x to a power, not 1 over x to a power, or 5 or a square root of something. You have to write it as just x all by itself raised to some power. So we're going to rewrite this first. Notice that when I'm rewriting it, I'm not writing f prime of x. I'm not taking the derivative yet. I'm just rewriting my function, which is not the same as its derivative. So I'm saying f prime of x is x to the 10th plus x to the negative 3rd plus the 5th root of x squared is x to the 2/5 power. And now we can take the derivative using the power rule. So now the derivative f prime of x is going to be 10 times x to the 9th plus negative 3 times x to the negative 3 minus 1 is negative 4 plus 2/5 times x to the, if you don't want to do the math right away, you can just write 2/5 minus 1 But then we should simplify that because we can. This is 10x to the ninth minus 3x to the negative fourth plus 2/5 times x to the 2/5 minus 5/5 is negative 3/5. So there's our derivative. Just throwing the power rule at it. Or we might have something like, okay, so I'm going to tell you, the way I actually prefer to write derivative problems is not like this. I don't like writing, here's the function, and then here's the derivative of that function. Another way of expressing this is to say something like find d dx of 5x to the seventh plus 6 times the square root of x plus 8. So this symbol here means take the derivative of whatever comes after it. It's kind of like this is my y, and I'm writing dy dx, or d dx of y. Okay, so that's going to be derivative of 5x to the seventh is going to be 35x to the sixth. Oh, I should have rewritten, but I didn't, so I'm just going to say, I know that the square root of x, I'm thinking of that as x to the 1/2, or 6 times x to the 1/2. So the derivative is going to be 6 times 1/2 times x to the 1/2 minus 1 is negative 1/2. And the derivative of 8 is 0. And then I'm going to simplify just a tiny bit. This is going to be 35x to the sixth plus, you can either write this as 3x to the negative 1/2 or 3 divided by x to the positive 1/2. Either way is valid. Either way is useful. Sometimes they have different purposes. I'll point out, we just used a rule that we never talked about. We use the constant multiple rule. If you take the derivative of a constant times a function, the constant just sticks around, and you take the derivative of that function, you multiply them together. What I really did here without saying it is I said, oh yeah, the derivative here is going to be 5 times 7x to the sixth. And then we multiply the 5 times the 7. And I'll say this a lot when you're taking derivatives or limits or in 21B integrals, constant multiples hang out. And they get multiplied by whatever you have, whatever derivative or integral, whatever you've taken. How much time? How much time? Sure. So let's get another example here. Sure. So if I wanted to find y prime for y equal to 6x cubed plus 4x plus 3 divided by 2x squared. And if I didn't know the quotient rule yet, or even if I did, I still wouldn't use it. Because in this case, if you have a quotient where you have a single term in the denominator, it's much easier to just divide each thing by that single term and simplify it first. So here we're going to simplify first and say, okay, y is equal to 6x cubed divided by 2x squared plus 4x divided by 2x squared plus 3 divided by 2x squared. We're going to rewrite it again. That's going to be 6 divided by 2 is 3. X cubed divided by x squared is x. 4 divided by 2 is 2. X divided by x squared is x to the negative first. 3 divided by 2, you can't do anything about that, just 3 halves. But dividing by x squared is like multiplying by x to the negative 2. Okay, so now we can find y prime. The derivative of 3x is just 3, because the derivative of x is just 1. The derivative of 2x to the negative first is 2 times negative 1 times x to the negative 1 minus 1, which is negative 2. And then over here we have 3 halves times negative 2 times x to the negative 2 minus 1 is negative 3. I would like to simplify this. It's going to be 3 minus 2 times x to the negative second minus 3 times x to the negative third. Yeah. So I'm kind of torn. In my mind, this brings up 2 important questions. How do we know the power rule really works for these other powers? Like, yeah, I said it, and I'm not a liar. I wouldn't lie to you about that. But like, it would be nice if we knew. So often people will do a couple examples showing how the limit definition still works for some other powers. Like, for example, someone might say, use the limit definition to find f prime of x for f of x equal to x to the negative first. Now, we already know what the answer is going to be. We know the derivative is going to be negative 1 times x to the negative 2. Well, let's show it. I also want to point this out because often it's a test question, right? This is a good example of something people like to ask on a test. So our derivative is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. And then we plug in. So our f of x plus h, I would much rather write this as, instead of x to the negative 1, as 1 over x. So my f of x plus h is 1 over x plus h. Our f of x is 1 over x, and all that's divided by h. And unlike the previous examples, I can't just like multiply it out and have the things that I want to cancel. I have to do other work here. I have to get a common denominator. So I'm going to multiply my 1 over x plus h by x over x, and my 1 over x by x plus h over x plus h. We do that, let's see what we get. We're going to get the limit as h approaches 0 of x over x times x plus h minus x plus h over x times x plus h. And to not have fractions in fractions, which is always never my favorite, instead of dividing by h, we're going to multiply the whole thing by what? By 1 over h. Right? Dividing by h is equivalent to multiplying by its reciprocal. Then we can combine those two fractions there. Here's a place where, again, you have to be a little extra careful. When you combine these two fractions, your denominator is x times x plus h, right? That's what we got, a common denominator. And the numerator is x minus parentheses x plus h. Simplifying, the x minus x is going to be 0, and the minus h will give me a minus h on top. And the denominator, I have x times x plus h times h. Multiply by 1 over h, I can just put that h in the same denominator if I want to. It's the same thing. Those h's cancel. So I have the limit as h approaches 0 of negative 1 over x times x plus h. Now I plug in 0, I get negative 1 over x times x plus 0, which is just negative 1 over x squared, or if you prefer, negative 1 times x to the negative second. So definitely the power rule does work for these negative powers as well. You can do something worse, like for x to the negative second. So did you get worse the further away the powers get from zero, from positive? Like a negative second power is a much worse process. A negative third power would be even worse, but it's still doable.
What did the h?
So I divided here. I said that this negative h divided by this positive h became negative 1. Another very common example in this same vein is either for the square root or the cube root. So I'll point out, yeah. So for f of x equal to the square root of x, you would do the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. I'm not going to do this one, but I'm going to ask you all, what would be my next step? Conjugate. I definitely think it is worth all of your whiles to do this one on your own. At the end of the day, you should get 1 divided by 2 root x. Or if you prefer, 1/2 times x to the negative 1/2, which again is what you would get using the power rule. Because the square root of x is x to the 1/2, and the derivative is 1/2 times x to the 1/2 minus 1, which is negative 1/2. I want to show you one that's worse. because I think you can all do this one, and you might get asked to do this on your exam. It's definitely a very reasonable question. People like to ask it. It takes a little bit of effort, but not too much. But this next one, you probably won't get asked to do, but I do think it's worth seeing. So let's look at one we've already talked about, the cube root of x, or x to the 1/3. I could see one of your teachers asking you this question. No, specifically, I think. He seems like he likes to ask complicated questions. Sorry. So here's what we're looking at. And I should write f prime of x. Sorry about that. So we're looking at the cube root of x plus h minus the cube root of x all divided by h. And we are going to multiply by something that kind of acts like the conjugate, but it's a little bit different. Here's what we're looking at. And we're going to come back to this in just a second. So here's the idea. We would love to not have those cube roots. So if we could cube both of those, we'd be really happy. The cube root of x plus h cubed would just be x plus h. So we really want to multiply this by something that's going to give us just like the first thing cubed and the second thing cubed. Here's what we want. We're going to take a minus b. Actually, no, we're not. We're going to take a cubed minus b cubed and factor it as a minus b times a squared plus ab plus b squared. We talked about this a little bit before about how you factor a difference of cubes. So the idea here is we're going to let a be our cube root of x plus h and b be our cube root of x. We're going to multiply it by our a squared plus our a times b plus our b squared. And then we're going to get back the cube root cubed minus the other cube root cubed. So the numerator will be nice and nice, and the denominator will terrible garbage, but it'll work out. So here's what we're going to multiply by. Check this out. You might not want to write this down. It's kind of awful. We're going to multiply by, well, I want to see this though. So we're going to multiply by our a squared. So it's going to be the cube root of x plus h squared plus our a times our b. So the cube root of x plus h times the cube root of x plus our b squared, which is the cube root of x squared. All divided by the same thing. I'm going to write the denominator so it looks a little bit nicer. I'm going to write the denominator. This is really x plus h to the 2/3 power plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3 power. Okay, so here's the part where I wish I could skip it, but I feel like I shouldn't. What should happen on top is you just get that cubed minus that cubed. But invariably, someone wants to see the work, which is totally fine. I understand not believing it's just going to work out. So let's do it real quick. So you get the limit, as h goes to 0. Okay, so let's see. So I have x plus h to the 1/3 times x plus h to the 2/3, which is going to be x plus h to the 3/3, which is x plus h. And then I'm going to have the cube root of x plus h times, so this times that, this times that. That's going to be x plus h to the 2/3, right? I've got a 1/3 and a 1/3, and then an x to the 1/3. And finally, the last one, x plus h to the 1/3 times x to the 2/3. And then the minus ones, minus x to the 1/3 times x plus h to the 2/3. Minus x to the 1/3 times x to the 1/3 is x to the 2/3 times x plus h to the 1/3. Finally, x to the 1/3 times x to the 2/3, which is x to the 3/3. All divided by h times all that. Sorry, I'm not saying the words. There we go. Plus that. Okay. Okay, now look at what happens on top here. X plus h to the 2/3 times x to the 1/3 cancels with negative x to the 1/3 times x plus h to the 2/3. And x plus h to the 1/3 times x to the 2/3 cancels with negative x to the 2/3 times x plus h to the 1/3. And x minus x also goes away. So I'm left with h. So we're left with limit as h goes to 0, this single h that's left behind divided by that h is 1. So we really have 1 over x plus h to the 2/3 plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. Letting all the remaining h's go to 0, we get 1 over x plus 0 to the 2/3. X plus 0 to the 1/3 times x to the 1/3 is x to the 2/3. And another x to the 2/3. If you add something to itself 3 times, you just are multiplying that thing by 3. So you have 1 over 3 times x to the 2/3, or preferably 1/3 times x to the negative 2/3, which is the derivative of x to the 1/3 power. The power came down in front. The new power is 1/3 minus 1, which is negative 2/3. Do you have to do this? Probably not ever. But that is a probably not a guaranteed not ever. So I'm not your teacher. I don't know what you might be asked, but it's good to have seen this at least once. So now you can really be like, oh yeah, the power rule really does work for any power. Yes, I know we haven't shown it for every power, but I think you can believe at this point, yeah, the power rule works. Make sure you're comfortable using it. We didn't get to talk about the product or the quotient rule, so that's on the docket for Thursday. You should definitely probably have already seen those in the class. Start using them, thinking about them. And have office hours as usual.